358 and 359. This is a continuation of Activity 1, the Inscribed Angles Theorem. Right? So please make sure that you have, open your book to those pages. You're going to need the following note cards. And so I've set this up in the previous video. Here we are again as a reminder. Make sure you have congruent radii in a circle. Make sure that you have the note card substitution property. We've been using this one over and over, and it is absolutely in use today. Make sure you have exterior angle theorem, and then there's the back for that one. Of course, at any time, pause the video, slide it over so you can get a chance to write down what's been posted. Isosceles triangle base angles theorem. All right, two more. In the intercepted arc, which means that the central angle in a circle is equal to the measure of the intercepted arc. And then the last one, the division property of equality. Basically, if you have an equation and you divide the right side of the equation, you have to also divide the left side. All right, so have those note cards ready to go because I'm going to be using them in the proof that we're going to complete on page 159. Do you have something to write with? Do you have something to write on? We're talking about the inscribed angle theorem. It's definitely the learning goal from page 355. Determine the measures of arcs, central angles, and inscribed angles. And we can determine because we have access to some proofs. Let's take a look. You've already got some notes from what we did in the previous video from the beginning of this one. And so we're going to just go ahead and carry on from here with what we need for the next problem. We have to prove your conjecture that the measure of the inscribed angle is half of the measure of the intercepted arc. You must prove each case. And by cases, we're going to be looking at what's happening from the three cases we have here, where one of the chords goes through the diameter, or is the diameter, or the intercepted arc is created by an inscribed angle where the center of the circle is in the interior of that inscribed angle, or this third case where the inscribed angle is created where the center of the circle is on the exterior of the angle. And so that's what we have right here. MPT is inscribed in circle O, and point O lies on the diameter PM. So just checking for a minute, we have MPT. It is an inscribed angle. So just a little bit of checking our given statements. That absolutely is true. Then we have that PM is actually the diameter. Like O, the center is a circle, is on that chord. Now what we need to do is prove that the measure of the angle MPT, this angle, is actually half of this intercepted arc. So here we go. All right, let's go. We have a worked example on the top of page 359. Let's take a look at that one. Here we go. You can use a construction and algebraic reasoning, so division property of inequality, to create a proof plan. Let's consider how to prove that the measure of this inscribed angle MPT is half of the measure of the inscribed or of the intercepted arc MT for case 1. Case 1 being like it's shown right here. So one thing that they do is they label MPT with an X. So there we go. We have an X that's created there. And you know what? The way that they labeled and then drew this radius, remember, all radii of a circle are congruent. So with a little bit of highlight action, OM, OP, haha, it's OP, and OT are all radii of that circle. So they are the same length. That'll probably come up somewhere along the way. Actually, right here, where they say that the triangle OTP is isosceles. OTP, that triangle is isosceles. That means there are base angles that are congruent. So if we have an X at angle P, we also have an X at angle T. And then, last of all, since MOT is double X, how is that possible? This is possible right here. We can say that MOT is 2X because there is this theorem that says the exterior angle of a triangle is double or is adding up the remote interior angle. So these interior angles here equal that exterior angle. And if you have an X right there and an X right here, they add together to make 2X. Therefore, this angle, MOT, creates an intercepted arc that is the exact same expression. So these are both 2x because the central angle and the intercepted arc are supposed to be exactly equal in measure. Then the fact that there's a 2 in here, whatever x is, the fact that there's a 2 here means it's going to be twice the size of that angle. 2x doubling a single x just the way that it is. The 2x means that we have a double, so therefore in reverse action, if you know how big the intercepted arc is, then you get to say that that angle is half as big. 4 to 2, 2 to 1, 60 to 30. That's the relationship. We need to now take that information and plug it all in. Oh, by the way, there's the proof. Therefore, boom and or boom. Okay, our proofs identified in the green and our givens up above in yellow. Let's go ahead and actually create a formal proof. And before I do, I kind of want to sketch out or at least lay out these cards in a flow proof given the worked example. So again, intercepted arc, division property of equality, congruent radii in a circle, isosceles triangle base angles theorem, substitution, and the exterior angle theorem. And we start with the givens. The givens are already provided, so I'm not really going to worry about that one. But I want to acknowledge right away that in order for us to say that we have an isosceles, right, it kind of looks like they showed this line being drawn. This is all step 0. These are the givens. This looks like step 1. We have to show that the triangle in here is isosceles. And the only way we can show that it's isosceles is if we set up that the circle's radii are congruent, in that OP and OT are the same. So this is the first thing that we need to do. We need to make sure that we establish this dotted auxiliary line that was drawn after everything was set up is making us think of radii. They are congruent. In fact, I should put a little spike. Boom, boom. Okay, so that's first. Now the next one. Once you know they're isosceles, we can then say, because we know that we have radii that are equal, this triangle is going to create angles that are congruent. So from congruent radii, the next thing we get to say is that the triangle that's created here has created equal angles because it's isosceles. All right, okay, so we do a little bit of setup. All right, you kind of look over here. That was step 2. Now, since we have the structure that we have these base angles, I had to then come up with the fact that we should label x. So we're going to label this x in there, and we're going to therefore say OTP, this angle down here, with the substitution property. Base angles are the same. You might as well call both of those angles by the same letter. Call them both orange x. Okay, so that's 1, 2, 3. Next up, when you know the 2 remote interior angles of the circle are added together, they're going to equal the exterior angle. So this is step 4, right there. Exterior angle theorem happens in the 4th position. Okay. Next up, if we're able to say that this central angle is 2x, then the arc out on the end is going to be the same amount. And that is because the intercepted arc is going to be equal to the central angle's measure. So we have intercepted arc as the 5th reason along the way. And then last of all, doing a little bit of division and then follow it up with some substitution, we can finish out this proof. So I'm going to add these note cards. I guess I'm going to reshuffle the order. Substitution, then division, working from the bottom up. Intercepted arc, exterior angle theorem, substitution, isosceles, congruent radii. I'm going to put this as my 3rd reason. Okay? Reason number 3. Congruent radii in a circle. Then I'm going to put this as my 4th reason. Isosceles triangle base angles theorem. Then I'm going to say this one for statement number 5, substitution. Remember, that was like you put an x on the other angle since you know the angles are the same. Substitution. Let me slide up my notes. Put the cards over here. Okay, now we're going to talk about exterior angle theorem as number 6. Okay. Since the exterior angles creates an exterior angle that is equal to 2x, and that central angle is the 2x angle, so is the intercepted arc out on the edge, because the central angle is equal to the measure of the intercepted arc. So statement 7, intercepted arc. And then step 8, once we know that there's a 2 involved, we should probably divide by 2. So we're going to have a division property of equality. And then in the very last step, because there's going to be some like equals x thing, we're going to have multiple statements. We got to tie it all together, and you tie multiple statements from the proof together using substitution. Now, those reasons need to go with accompanying statements. And sometimes, maybe I did this backwards from the way you were thinking about it, or the way that I was explaining it, but I wanted to make sure that I used my note cards and shown you that they had an intentional use. You need to be making them so that you can do that shuffle with them. On the back of the note cards can be example statements. So something that I'm going to do is I'm going to take the congruent radii in a circle, which doesn't have an example on it yet, and I'm going to use what I write in statement 3 as my example so that for the future, when this pops up, I have a matching statement on the back that I can look at and help remind me of what I'm supposed to say. So using the diagram, using the fact that statement 3 and reason 3 have to match, I'm looking at showing what I highlighted yellow. OP and OT are congruent. That needed to be identified, all right? Now, next up, statement 4, right? Statement 4 is the isosceles triangle base angles theorem. Let me move this recording over to here. Okay, so the isosceles triangle base angles theorem, we get that because these two angles have to be the same. Since you have an isosceles triangle, then in statement 4, that tells us that angle P, I should use 3 letters, OPT is congruent to OT, the other one, the other side of the thing. Okay. Congruent to OTP. Pay attention to the middle letter, right? The middle letter in the group of 3 is what we need to show that they're actually like the angle we're focused on. Okay, now we're going to do some substitution, right? So some substitution is going to let us acknowledge that we can just replace an x with OTP. So we have an x right here, right? It's been mentioned the measure of MPT is x. Here's where orange happens in our proof. We also have the radii are created. So I've already created the radii in yellow here. Okay, new goal is to also say that if these two things are the same, and MPT, this one, x right here, I guess it's OPT in my notes, okay, I put an O instead of an M, that this angle is x, then so is the other one. The measure, by substitution, the measure of angle OTP also equals x. So that's another orange that's happening. Okay, next up we have the exterior angles theorem. So in the next up we have the exterior angles theorem. So since these two angles are the remote interior angles, they must add together to make 2x. So that's what we're going to do. For the exterior angle theorem, we're going to identify that the measure of angle MOT, that's this one, is 2x. Pink. Okay, now we bring in intercepted arc as statement 7. This shown the diagram, this 2x and this 2x are the same because the central angle has a measurement that is equal to the intercepted arc's measurement. So 7 is going to tell us that the measure of arc MT is also 2x. That's another pink. Pink because I highlighted that way on my diagram. Okay, since we have MT is 2x and MOT is 2x, and you add up x plus x to make 2x, then we can use the division property of equality to divide both sides of this by 2. Or actually, it is division, but did you know that division and multiplication of a fraction is the same thing? So I'm going to divide by 2 to produce x, but I'm also going to then put MT in front of the fraction 1/2. 1/2 and division are by 2 are the same. M of arc MT. Now, last of all, we've got some more substitution because here's an x, here's an x, here's an x, here's an x. That's going to tell us that OPT, that arc right there, is equal to half of the intercepted arc. So 9, we're going to replace the x with what it's equal to. M angle OPT equals half M arc MT. We're done. Why do you think the proof of this theorem requires the proof of 3 different cases? Can't we just apply this proof to all of them? Why is it important to consider a proof for the diameter, for when the center of the circle is in the interior of the angle, or when the center of the circle is on the exterior of the angle? Remember, which theorems did this proof use? We used the isosceles triangle base angles theorem. We used the exterior angle theorem. And then we are using these properties, but those two right there, there was a whole other 2-column proof that we could have inserted into this section and into this section. Like, we could have totally rewritten step 6 as one gigantic extra 9 steps. But by using our shortcuts, cheat code, open it up, we can use the theorems to take 7 steps that we did somewhere else and compress them down to 1 step right now. How do you know triangle OTP is isosceles? Reflect on that. How do we know that this triangle is actually isosceles? I answered it. Do you remember? And last of all, how does knowing that triangle OTP is isosceles help you determine the relationship between the 2 angles, OPT and OTP, these x's that I highlighted orange? How does knowing that that triangle is isosceles give you some clarity on the relationship between those 2 angles? Food for thought. Thank you for doing some math with me. Thank you for sticking it out to the end of the video. Appreciate what you are learning and doing and growing along the way. Don't forget to like, comment, and subscribe. Psych. And I'll see you on the next video. Thank you. Bye.